Welcome. My name is Brian. This is a reading of the most well-written datasheet I've ever seen. Enjoy. Supply Voltage Supervisor TL77 Series. Author Eilhard, Haseloff. Literature number SLVAE04, March 1997. Introduction. After power on, a digital system must normally be forced into a definite initial state. For microcomputers and microcontrollers, a reset input is provided to which, in simple applications, an RC network is connected. After power on, the circuitry maintains the logic level at its input high or low until the supply voltage has reached its nominal value, and the internal logic of the microcomputer has executed the initialization of the system. However, this circuit does not work well during short drops of the supply voltage. In this case, the capacitor must be quickly discharged via the diode, which will occur only if the supply voltage goes below the threshold voltage of the reset input. A small decrease of VCC under the recommended minimum supply voltage can destroy the content of memory and registers and yet not activate the reset circuit. This may have catastrophic consequences. The following program example, 8080 assembler code, tests an input. If, during the execution of the loop, the content of the BC register is affected by a short voltage drop, causing an incorrect input to be read, an incorrect condition will be tested and an incorrect decision will be the consequence. Alternatively, the addressed input will show a value which can never give a positive test result. The execution of the program seems to be stopped. In larger computers, several features are provided to prevent such errors. A power fail interrupt signals dangerous conditions in time, the content of the memory is protected by battery backup, and so on. In small microcomputer systems, this amount of effort is too expensive, and in most applications is not required. It is usually sufficient if, after a serious voltage drop, the microcomputer is forced into a defined initial condition. To implement this function, whilst preventing the problems mentioned above, the following circuit features are required: accurate detection of a serious voltage drop, generation of a reset signal while the supply voltage is not in the operational range to prevent undefined operations of the microcomputer, maintenance of the reset signal for a certain time after the supply voltage has returned to its nominal value to ensure proper initialization of the circuit. For these applications, Texas Instruments has developed a series of integrated circuits which, with a minimum of external components and without additional adjustment, will fulfill the requirements described above. Two, circuit description. The main part of this circuit is a reference voltage source which consists of a very stable temperature compensated band gap reference. An external capacitor, typically 0.1 microfarad, must be connected to the voltage output to reduce the influence of fast transients in the supply voltage. The voltage at the sense input is divided by a resistor divider and compared with the reference voltage by a comparator. To achieve high accuracy, this divider is adjusted at wafer probe. When the input voltage is sensed to be lower than the threshold voltage, the thyristor is triggered, which discharges the timing capacitor C. It is also possible to fire the thyristor via RESN input by the logic level, TTL level active low. The thyristor is turned off again when either the voltage at the sense or the RESN input increases beyond the threshold, or during short supply voltage drops, the discharge current of the capacitor becomes lower than the hold current of the thyristor. Thereafter, the capacitor is recharged by a current source, 100 microamps, the charge time being calculated as follows. The magnitude of the charge current, and therefore also the delay time, is determined by the tolerance of the resistors in the integrated circuit. These tolerances, caused by the semiconductor manufacturing process, are not negligible. Therefore, the delay time may vary from negative 50% to plus 100%. However, for the applications discussed here, this will not be a restriction. The diagram in Figure 3 shows a typical delay time versus the capacitance of the external capacitor. An additional comparator compares the voltage at the capacitor with the reference voltage and forces the outputs in the active state as long as the voltage at the capacitor is lower than the reference voltage. Figure 4 shows the timing of the various signals. In this example, the sense input is connected to the supply voltage VCC, as in typical applications of this device. The minimum supply voltage for which the function of this device is guaranteed is 3.6 volts. After power on, the outputs are undefined until the minimum supply voltage Vres is reached. For the TL77A, the minimum supply voltage is 3 volts, typically 2.5 volts. For the TL77B is 1 volt. Also, when using the TL77B, it has to be noted that with such low supply voltages, the function of the reset input of the following circuit may not be guaranteed. Beyond the voltage Vres, the capacitor C is first kept discharged and the outputs stay in the active state. Reset equals high, reset equals low. When the input voltage becomes higher than the threshold voltage, Vt, the thyristor is turned off and the capacitor is discharged. After a delay, the voltage at the capacitor passes the trigger level of the output comparator and the output becomes inactive. The circuit to be initialized is now set to a defined state and starts the correct operation. The thyristor is triggered again during the voltage drops below the threshold voltage, and the reset sequence starts again. Also now the output stays in the active state for the time t after the return of the supply voltage to its required value. A hysteresis VH at the initial comparator prevents oscillation of the input circuit when the input voltage rises or falls slowly. The time D and also capacitor C are determined by the requirements of the following circuitry in TTL or CMOS circuit logic circuit. The time TD and also the capacitor CT are determined by the requirements of the following circuitry. In TTL or CMOS logic circuits, theoretically, a reset time of 20 to 50 nanoseconds is sufficient. For proper operation, microcomputers require a reset signal which lasts for several machine cycles and is thus in the order of 10 to 200 microseconds, according to the type of microcomputer in use. In a practical application, the delay time will be determined by characteristics of the power supply. Care has to be taken that during and shortly after power on, short voltage fluctuations do not repetitively reset the system. Delay times of 10 to 20 milliseconds or even up to 500 milliseconds will usually avoid these problems. Owing to an internal limitation of the discharge current of the timing capacitor CT, there is no upper limit to the size of this capacitor. Application examples. 5 versions of this circuit are available. TL7705A and B, 4.55 volts. Application in TTL systems and microcomputer systems which require 5-volt supply, e.g. TMS7000. TL7709A, 7.6 volts, application in microcomputer systems using the TMS1XXXNLL. TL7712A, 10.8 volts, application in CMOS, microprocessor, and memory circuits with a 12-volt supply. TL7715A, 13.5 volts, applications in circuits which operate with a supply voltage of 15 volts, as is often found in analog circuits. TL7702A and B, 2.5 volts, application in systems where other supply voltages are used. The required trigger level may be adjusted with an external resistor divider at the sense input. Since for most applications the circuits are already adjusted to the appropriate voltage levels, these devices are easy to use. Figure 5 shows the initialization circuit diagrams for TMS 7000 microcomputer system with a supply voltage VCC of 5 volts. The external components required are the decoupling capacitor, CREF, for the reference voltage, and the timing capacitor, CT. These outputs of the TL77 are open collector outputs. In Figure 5, therefore, a pull-up resistor is shown at the reset output to ensure the correct high level. In larger systems, where several supply voltages are required, it is necessary to supervise all supply voltages, which may cause dangerous conditions in case of power failure. In the circuit diagram in Figure 6, two TTL12As are used to monitor the positive and negative 12-volt supplies. These outputs are fed into the RASN input of the TL7705A, which monitors the 5-volt supply. The output of this device provides a reset signal, which becomes active whenever any one of these three supply voltages fails. A reset signal can be generated manually via a switch, which is connected to the voltage monitor of the positive 12-volt supply. When designing a supply voltage monitor, the designer has to take care that when only one of the supply voltages becomes marginal or fails, a defined reset signal is generated, at least if the main supply voltage is 5 volts is still available. Therefore, the circuit which monitors a 12-volt supply voltage is supplied by the 5-volt supply. The reset signal of the circuit which monitors the negative supply is fed via a resistor divider to the base of the transistor BC546, which controls the RSIN input of the TL7705A. The voltage divider is designed so that a reset is generated even if the negative supply fails totally. The capacitor, which determines the delay of the two circuits which monitors both 12-volt supplies, can be chosen short. In the example shown here, it is 0.01 microfarad. The output of these circuits has only to trigger the third monitor, TL7705A. The final duration of the reset signal will be determined by the capacitor C of the last mentioned circuit. These supply voltage supervisor circuits were designed to detect supply voltage drops as short as 300 nanoseconds. In Figure 7, the minimum pulse width at the sense input shown versus the amplitude of the supply voltage drop, delta VCC, which is required to trigger the voltage monitor. The sensitivity of the other circuits, TL7702, TL7712, etc., can be calculated as proportional to the trigger voltage ratio. In applications where this performance is not required, sensitivity can be reduced by placing an RC filter in front of the sense input. To avoid unacceptable change of the threshold voltage of circuits with a fixed threshold voltage, the value of the resistor should only be a few 10 ohm only. In applications like this, it may be better to use a TL7702A. With this circuit, the threshold voltage can be set to the desired value by a high impedance voltage monitor. A small filter capacitor C at the sense input reduces the trigger sensitivity. Figure 8. In some applications, it is necessary to keep the output of the reset circuit active, even if no supply voltage is applied. Under normal conditions, the output transistor of the TL77A is turned off in active state. When the supply voltage is lower than 3 volts, in some applications it is necessary to keep the output of the reset circuit active even if no supply voltage is applied. Under normal conditions, the output transistor of the TL77A is turned off in active state when the supply voltage is lower than 3 volts. In Figure 9, a P-channel field effect transistor is connected to the reset output. This transistor conducts when the supply voltage drops below 3 volts, i.e. at the gate source voltage of -3 volts or less. To ensure that the transistor is switched off when the supply voltage has reached the nominal value, the gate has to be at least 6 volts more than the positive source, or the required high level, e.g. 2.4 volts. In Figure 9, therefore, the voltage monitor is supplied by supply voltage of 12 volts. Since the requirements for the supply voltage in terms of stability are not high, this supply voltage, for example, can be taken from the filter capacitor in front of the voltage regulator in the power supply. A further application of these integrated circuits is in battery buffered memory systems. When the line voltage fails, the content of the memory must not be corrupted by a random write operation of the microcomputer. These uncontrolled write operations may take place at low supply voltage, even if the reset signal is applied to the processor. Generally, it is sufficient to switch the chip select line into the inactive state. Some memories require that the write line also be disabled. A switch, which consists of transistor Q and diode D, is inserted into the chip select line of the memory. Under normal operation, voltage line present, the output of the TL7705B is turned off, high. The transistor Q draws its base current from transistor Q and resistor R. When the chip select line is switched from high to low by the supervising microprocessor, the transistor conducts and the chip select input of the memory goes low and the memory is enabled. Because of the small DC load of the resistor, the saturation voltage of the transistor, and therefore the shift of the low level to the chip select input, is very small, typically 40 millivolts. When the chip select line is switched high again by the processor, the transistor Q is turned off. The influence of the inverse current gain is negligible. The diode D conducts and charges the circuit capacitance. In the case of a power failure, the TL7705B is triggered and its reset output becomes low. The base of the transistor Q can no longer draw current. Thus, the chip select input of the memory is separated from the chip select line. As has already been mentioned, the supply voltage supervisors of the series TL77A incorporate extremely stable reference voltage sources which can be accessed at the VREF terminal. This voltage source can also be used when in other applications a constant voltage source is required. As shown in pictures 11, the reference voltage, Vref, varies less than 10 millivolts when the supply voltage is changed from 3.5 to 18 volts. The same stability of the reference voltage is maintained when the ambient temperature is changed. Figure 12 shows the typical characteristic. The reference voltage varies only 16 millivolts when the ambient temperature is changed from -40 to 85 degrees Celsius. When using the integrated reference voltage to supply other circuits, the designer has to consider that the maximum current available from this voltage source is in the order of 100 microamps only. With higher loads, the stability of the reference voltage suffers. For higher currents, a buffer in the form of an operational amplifier connected as an emitter follower is recommended. Figure 13. If the voltage monitor section of the circuit is not used in this application, the capacitor C is not required. This terminal may then be left open. The inputs sense and RES in are connected to ground. Four, design tips. The application of the supply voltage supervisors of the series TL77 is not complicated. However, it should be noticed that this circuit is an analog circuit, whose function and performance, meaning the stability of the reference voltage, may be negatively influenced by noise in neighboring circuits. Therefore, the voltage monitor should be placed on the printed circuit board where there are no neighboring circuits in which switch high currents, like bus interface circuits or power switches. When laying out the layout of the printed circuit board, special care should be taken with the interconnects which carry analog signals. Besides the sense input, these are the C and V ref terminals. Noise coupled to the C input will lead to a reduction of the output pulse width. Noise coupled into the VF input or into the filter capacitor at this input may lead to undesired triggering of the circuit, and by this to an undesired reset. Practice shows that this malfunction when high currents flow over the interconnects of these capacitors to the ground terminals of the voltage monitor. To avoid these effects, the ground terminals of these capacitors must be connected by the shortest way to the ground terminal of the voltage monitor, and so that no currents caused by other circuits flow over these wires. Figure 14 shows a layout proposal for the printed circuit board. Furthermore, the resistors of the voltage divider at the sense input of the TL7702, R2 and R3 in figure 14 have to be placed in so that no noise may be coupled into the circuit. When using the Supply Voltage Supervisor TL7705B, in certain applications a current limiting resistor in series with the capacitor is required. With this circuit, the timing capacitor will be charged up to the supply voltage VCC respectively, and internal clamping 7.1 volts, where the smaller of these two voltages determines the final voltage of the capacitor. When the supply voltage drops quickly down to a voltage which is lower than the current voltage at the capacitor, a parasitic current may be turned on, which in turn erroneously activates the outputs. This effect is avoided when mentioned parasitic current stays below 1 milliamp. Considering this, the resistor is calculated as follows. To a small degree, the resistor influences the time delay. In most applications, however, this effect can be neglected, because when determining the length of the reset pulse, a large reserve is taken into account. When designing a supply voltage supervision circuit, often an analysis of the noise on the supply lines is required. The probes of the oscilloscope usually used for this kind of measurement mostly are not capable of performing the measurements correctly. The main reason is the ground wire attached to the probe. This wire often acts as an antenna which receives all the noise generated by the surrounding circuits. This leads to a wrong display on the oscilloscope screen. More accurate results are found when the signal to be measured is taken via a 0.1 microfarad capacitor to block the DC voltage, directly soldered to the point of the measurement. The other end of the capacitor is connected to a coax cable whose shield is connected by the shortest path to the next ground reference point. The coax cable leads to the input of the oscilloscope, where the cable has to be terminated correctly to avoid line reflections. Summary. Monitoring the supply voltage is absolutely mandatory to guarantee a correct initialization of the circuit and to detect undefined operating condition, e.g. an undervoltage. This report shows several application examples for the supply voltage supervisor circuits of the TL77A. Owing their very accurate threshold voltage, they can be easily designed into systems replacing expensive discrete circuits. Thank you.